This video looks at the first derivative test, and basically what the first derivative test tells us is where we have a relative minimum point and where we have a relative maximum point. And the idea behind the test is that we know that the derivative is telling us the slope of our tangent line. And if we look over here at the left, we can see that if we pick a point to the left of this red dot, and we'll say this red dot's representing our critical number, and over here to the left, we realize that if we pick any point on the graph, our tangent line is going to have a negative slope. And that simply means that our derivative is going to be negative. And of course, what happens at this point here, our critical number, we know that our tangent line is horizontal, so we have a slope of 0. And then all of a sudden our graph changes directions, so then our derivative here is going to be positive, which means the slope of our tangent line is increasing, so therefore our graph is going from decreasing and then all of a sudden it goes to increasing, and that tells us that we're going to have a relative minimum point. And similar over here on the right, we have just the reverse. Our graph is increasing, so our slope is positive, so that means our first derivative is positive. And then here at the critical number, our graph does change direction, because if we pick the slope of any tangent line to the right, it's going to have a negative slope, or the derivative is going to be negative. Now below here we have two other cases, and if you notice here we have our red dot representing our critical number, and to the left we have our graph, and we can see that the tangent line is positive. It has a positive slope, so therefore our graph is increasing. But what happens at the critical number is our graph doesn't change directions. It continues to increase because our tangent line still has a positive slope. And the same thing is true over here on the right, but now as we go along our graph, we have a negative slope, and we get to our critical number, our graph once again doesn't change directions and go back up. It continues to curve and go down, so therefore we have a negative slope. So what that means, our graph is always decreasing. Okay, so it's possible, we know that, of course, you're not always going to have a relative max or relative min. And here's two examples of where that could possibly happen. All right, let's look at this example here. How can we actually apply our first derivative test so that we can identify on this function where we have relative maximum and relative minimum points? Well, the first step is we need to find the derivative so that we can locate our critical numbers. So the derivative here would be 3x squared minus 12x. And remember, to find the critical numbers, we're going to set that derivative equal to 0. And here we could factor out a 3x, and we're left with x minus 4. And if we set each factor equal to 0, we set 3x equal to 0, and solve for x, we're going to get x equals 0. X minus 4, set that equal to 0, so therefore x equals a positive 4. So that gives us our two critical numbers. Now it's possible that we only have one, we could have none, or we could have 3 or 4 or 5. So in this case we have two critical numbers. And what we can imagine here is if we look at our x-axis, that tells us that at x is 0 and x is 4, these are points on the graph where we could possibly change direction. So we need to look at what's happening to the left of 0, what's happening between 0 and 4, and what's happening to the right of 4. And that's going to give us our test intervals. If we know what's happening here from negative infinity to 0, if we know that our slope is positive, then it's always going to be positive because our graph is not going to change directions until 0, if it changes at all. So then we figure out what's happening from 0 to 4, because again, our graph cannot change directions until 4. And then we want to know what's happening to the right of 4. So that's where we get these 3 test intervals. So our test intervals would be negative infinity to 0, and then we have to go from 0 to 4. Okay, so we always got to check in between our critical numbers. And then we're going to go from 4 to infinity. So then at this point, we have to pick a test point. So we need to pick any number from negative infinity to 0. And I always say keep it simple. So I'm going to pick negative 1. And then we need to pick another point from 0 to 4. So I would simply pick positive 1. And then 4 to infinity, I would simply pick 5. Now we need to take this number and find out what is the slope at that point. Now remember, whatever the slope is at negative 1, that's going to be the slope of the tangent line at any point. Well, it's going to be positive or negative from negative infinity to 0. So if we take the negative 1 and plug it in to the derivative, now be careful, we're plugging the negative 1 into the derivative, so that's 3 times negative 1 squared minus 12 times negative 1. And if we do that, again, we don't really care about the value of the number. We just want to know, is it going to give you a positive or negative? And we will discover if we plug that in, we end up with a positive number, which means we have a positive slope. So that tells us from negative infinity to 0, our graph is going to be increasing. Okay, so from negative infinity to 0, that's kind of our conclusion. It's positive, so we're going to be increasing. Now, what happens if we evaluate the derivative at 1? So 3 times 1 squared minus 12 times 1, we end up with a negative number. Well, if we have a negative number, then that means our slope, our tangent line, our graph then would be decreasing. And then our final interval, we need to plug in for 5. And again, this is the derivative. Plug 5 in to the derivative, 3 times 5 squared minus 12 times 5. We end up with a positive number. So that tells us then we can conclude that our graph is increasing. So if you notice here, from negative infinity to 0, our graph is increasing. From 0 to 4, our graph is decreasing. And from 4 to infinity, our graph is once again increasing. So if you notice, at our critical numbers 0 and 4, that's where we're changing directions. So that tells us then at the point where x is 0, and if we plug 0 now, if we want to know this exactly, plug 0 into the original function. 0 cubed minus 6 times 0 squared plus 15 is 15. So at 0, 15, we have a relative max because our graph is increasing and then decreasing. And what happens at 4? Well, when x is 4, if we want to know the y value, we plug 4 into the original function. And if we do that, we'll find out it to be negative 17. So that tells us at this point, because our graph is decreasing and then it changes to increasing, we end up with a relative minimum. Okay, so based on our derivative, what this tells us is if our graph is increasing from negative infinity to 0 at any point, it's always going to be positive from negative infinity to 0. So I mean, if you went up here and you picked another point, you could pick negative 2 or negative 20 or negative 2000. And if you plug any number in this interval, it's going to give you a positive slope. So therefore the graph is increasing. And that's because our critical numbers tells us where our graph could possibly change directions. So that's why if we have these two critical numbers of 0 and 4, we only need to test a number in each of these 3 intervals. And you can see this a little bit better if we look at the graph of our function. Down here on the right, we have the graph of our function, and you can see that our graph is always increasing here on the left until we get to our relative max, where our critical number, and then it continues to decrease until we get to our relative minimum here, which again, this is where we had our critical number. Okay, so this is our relative max at 0, 15, and our relative min at 4, negative 17. So that's why we only needed to test in the interval from negative infinity to 0, because if you notice, any point on this graph is going to have a positive slope. And then if we looked at from 0 to 4, if you look here, any point on the graph here has a negative slope until we get to 4, and then to the right of 4 the graph is increasing, so every point has a positive slope. And this here is actually the first derivative test. You simply find your critical numbers, you come up with the test interval, plug in the test point into the first derivative, and that's where you determine if your graph has a positive or negative slope, which then tells you whether your graph is increasing or decreasing. Okay, we have one more example to look at. And again, we want to use our first derivative test to identify our relative max and relative min. So the first step is we need to find the derivative. And you'll notice here, x minus 1 to the 1/3 power. We're going to have to use the chain rule. So that's 1/3 times x minus 1. And if we take 1 away from 1/3, we end up with a negative 2/3. And now we need to multiply by the derivative of the inside. So the derivative of x minus 1, well, that's very simple. The derivative of x is simply 1. So you really don't even need to write that, but I just want to remind you here that we are using the chain rule. So there's the derivative, and now we need to set this equal to 0 to find our critical numbers. And when we're solving this equation, I think you're going to find it easier if you make your exponents positive. So you really notice that we have 1 over 3 times x minus 1 to the positive 2/3. So if we move the x minus 1 to the negative 2/3 to the denominator, our exponent becomes positive. So now the question is, when does this equation equal 0? Well, I hope you notice here that if we multiply both sides of the equation by 3 times x minus 1 to the 2/3 so that we can get this piece out of the denominator, once we multiply over here on the left, it's going to disappear, but if you multiply it to the right, it's still going to be 0. So we're going to end up with 1 equals 0. So what that tells us is this equation will never equal 0. Okay? Now, what happens though if we notice, because it's x minus 1 to the 2/3, what's the other place that we can have a critical number? Well, what happens when x is 1? If x is 1, we get 1 minus 1 is 0. 0 to the 2/3 is 0, so we end up with 1 over 0. So here we know that when x equals 1, it's undefined. So that tells us our equation is not differentiable at x equals 1. And remember, if your first derivative is equal to 0 or if it's undefined, if it's not differentiable at a point, that's going to give us a critical number of 1. So our critical number is 1 because it is not differentiable at x equals 1. So once again, if you think of this on a number line, if we only have one critical number, we simply divide our number line into 2 intervals, and that would be negative infinity to 1 and 1 to positive infinity. So then once again, we need to pick a test point. So any number to the left of 1, and I would make it easy on yourself and simply pick 0. And then a number to the right of 1, I would pick 2. And then we're going to take and evaluate our first derivative at 0. If we plug 0 into the first derivative, what's going to happen? Well, if you plug 0 in up here, you get 1 over 3 times 0 minus 1. Well, if you have 0 minus 1, you get negative 1 squared for the 2/3. So negative 1 squared is going to be positive. So you're going to end up with a positive 1 over a positive. So 0 is going to give you a positive number. So what does that tell us? Well, that tells us our tangent line has a positive slope. So therefore, our graph is going to be increasing from negative infinity to 1. Now we evaluate the derivative at 2. And if we plug 2 in, we get 2 minus 1, we get 1 on the bottom. So that's going to be positive on the bottom. The top's always positive. So once again, we have a positive slope, which we can conclude the graph is increasing. So here our graph is increasing from negative infinity to 1, and then it continues to increase from 1 to infinity. So therefore we have no relative extrema. And over here at the right, we can tell if we look at the graph of our function, if we follow along, we can see that our graph is increasing. Our tangent lines here, all of these would be positive. So as we go along the graph, it is always increasing. So therefore, there are no relative extrema. And again, that is showed to us with the first derivative test because, again, the only time our graph is going to change direction is at our critical numbers, and that means that we're going to have our graph go from increasing to decreasing or from decreasing to increasing. And this particular graph, it is always increasing, so there are no relative extrema.